Welcome to the deep dive. Ready to explore something pretty fundamental today?
Always.
Okay, good. Because today we're diving into the quantum nature of matter, specifically wave-particle duality.
Yes. The idea that everything, all the stuff we're made of, can be both a wave and a particle.
It might sound a bit abstract, I know, but it's actually crucial for understanding how the universe works at the tiniest levels.
And the really cool part is how this, seemingly complex concept is behind technologies we use every single day.
Exactly. And we're going to cover a lot of ground today, so get ready for electron waves.
Electrons, not just tiny balls, but also ripples, right?
Right. We'll see how that wave nature actually shapes the structure of atoms and how those atoms emit light.
Fascinating stuff.
They will impact lasers, delve into the light given off by really hot objects, and even get into the limits of what we can actually know in the quantum realm.
It's all connected, isn't it?
It is. All these topics, from how an atom stays stable to the focused beam of a laser, are different ways of seeing this idea that matter and light aren't just one thing or the other.
They have this dual identity.
Exactly. Okay, let's start with the very idea that particles can act like waves.
Yeah.
Back in 1924, Louis de Broglie, what sparked this radical thought?
Well, he was looking at the universe, and he noticed a kind of symmetry. Light, which we'd always considered a wave, was recently shown to act like a particle, the photon.
Right.
So he wondered, if waves can be like particles, could particles also be like waves? He proposed every particle has a wave connected to it.
And the wavelength of this matter wave depends on what?
It's inversely related to the particle's momentum, basically how much oomph it has.
Okay, so more momentum means.
Shorter wavelength. And something lighter or moving slower would have a longer wavelength.
So even like a baseball thrown at a certain speed has a wavelength.
Technically, yes.
Yeah.
But it'd be so incredibly small we could never actually observe it. It's pretty mind-blowing to think everything has this dual nature.
It is. It was just a theory back then, though, right? How did scientists actually prove electrons have wave-like properties?
They did it through electron diffraction experiments. Now, think about what happens when you shine X-rays, which are electromagnetic waves, through a crystal. The atoms in that crystal, they're arranged in a regular pattern. And this pattern acts like a diffraction grating. It makes the X-rays scatter and interfere with each other.
Okay.
And that interference creates a pattern of bright and dark spots, a diffraction pattern. The amazing thing is that when scientists shot beams of electrons at crystals, they saw similar diffraction patterns.
Really?
Yeah, it's like imagine shooting tiny marbles at a screen with two slits. Instead of just two lines behind the slits, you get this whole pattern of lines because the marble waves are interfering with each other.
That is a great analogy. And I remember there's even a specific way to calculate the wavelength for electrons accelerated by an electric field. Okay.
Yes, for a non-relativistic electron accelerated through a potential difference, let's call it VIBA, the wavelength is given by lambda, that's the Greek letter, equals h, divided by the square root of 2 times the mass of the electron times its charge times VIBA.
Complicated but cool. But these electron waves aren't just some weird theoretical thing. They have real implications, right? You mentioned atomic stability.
Absolutely. The wave nature of electrons is actually fundamental to why atoms don't just fall apart. Imagine the electron waves around the nucleus as needing to form these stable, standing waves.
Denby waves.
Yeah, like a guitar string.
Yeah.
It can only vibrate at certain frequencies to make those stable patterns. Similarly, electrons and atoms can only exist in specific energy states that correspond to stable wave patterns around the nucleus.
Okay, I'm starting to picture it.
Good. If the electron were just a particle orbiting the nucleus, classical physics says it should constantly lose energy and spiral into the nucleus super fast.
Which would be bad.
Very bad. But because it also behaves as a wave, it exists in these stable states, preventing that collapse.
So it's the electron's wave nature that keeps the atom from imploding.
Exactly.
And you also mentioned electron microscopes. I always thought that magnification was all about clever lenses. How do electron waves play a role?
Well, the basic idea of creating a magnified image does involve focusing a beam, sure. But resolution, how well we can distinguish between two very close objects, is limited by the wavelength of whatever we use to see them. Visible light has fairly long wavelengths. Electrons, especially when they're accelerated really fast, have super short de Broglie wavelengths, thousands of times shorter than visible light.
So that's why electron microscopes can see things that are way too small for regular microscopes.
Exactly. While the magnets in an electron microscope focus the beam to make a bigger image, it's the tiny wavelength of the electrons themselves that let us see those nanoscale details, stuff that's totally invisible with light microscopes.
That's a fantastic application of a pretty abstract concept.
Oh.
Okay, so electrons have wave-like properties. Now let's talk about atoms and the light they give off. We all know if you heat something up, it glows. What's going on there?
Right. Studying atomic structure is really all about understanding the light atoms emit and absorb. When you heat things up, the atoms gain energy, and they can release that energy as electromagnetic radiation.
Light.
Exactly. And if we take that light and pass it through a prism, we can see its spectrum.
Like a rainbow.
Kind of. It's a breakdown of the different wavelengths of light that are present.
Okay, and you said there are two main types of spectra, right? Continuous and emission line spectra. What's the difference?
So hot, dense objects like the filament in a light bulb or molten metal make what we call a continuous spectrum, like a rainbow smoothly blending all the colors, meaning it contains all the wavelengths of light.
Got it.
But if you heat a gas, it emits light only at specific wavelengths. This makes an emission line spectrum. Instead of a smooth blend, you see distinct bright lines at particular wavelengths.
And each element has its own unique set of those lines, right?
Yeah, exactly. It's like a fingerprint for that element. By looking at the light from a substance, we can tell what it's made of, whether it's a gas in a lab or a distant star. It's a powerful tool for understanding what the universe is made of.
Like atomic barcodes.
I like that.
So these lines of light give us clues about the structure of the atom itself. But before we get into how those lines are generated, let's talk about how we even figured out the basic structure of an atom in the first place. That leads us to Rutherford's gold foil experiment, right?
Yes. In the early 1900s, Rutherford did these groundbreaking experiments where he fired tiny, positively charged particles called alpha particles at a super thin sheet of gold foil.
And the idea was to see how those particles interacted with the atoms in the gold, right?
Exactly. The prevailing model of the atom back then was this plum pudding model. It pictured a diffuse positive charge with negative electrons scattered throughout, like raisins in pudding.
Interesting.
So Rutherford expected the alpha particles to pass through with just minor deflections.
But that's not what happened.
Nope. While most of them did pass straight through, some were scattered at huge angles. Some even bounced straight back.
Wow. What did they tell him?
It meant the atom's positive charge and most of its mass must be concentrated in a tiny, incredibly dense center. He called it the nucleus. And the electrons, he proposed, orbited this nucleus with mostly empty space between them.
It sounds like this discovery really changed how people thought about atoms.
It was a complete game changer.
But this model, based on classical physics,
Yeah.
had some problems, right? What were the main issues?
Well, according to classical physics, any charged particle that's accelerating, like an electron orbiting a nucleus, should constantly give off electromagnetic radiation.
Like, it should be losing energy constantly.
Yes. And as it loses energy, it should spiral into the nucleus very quickly, making atoms fundamentally unstable. But we know atoms are stable.
Right.
Plus, Rutherford's model couldn't explain why heated gases emitted light only at those specific wavelengths we talked about. Classical physics predicted a continuous range of wavelengths.
So, while Rutherford gave us the nuclear atom, something was still missing.
It was, and that's where Niels Bohr stepped in with his revolutionary idea of quantized energy levels.
So how did Bohr address these problems? What was his big insight?
He proposed that the energy of an atom isn't continuous, like a ramp. Instead, it's quantized, meaning it can only exist at specific energy levels, like steps on a staircase.
Okay, that makes sense.
Right. An atom can only have these particular energies, nothing in between. And he connected this to the light atoms emit and absorb. He said an atom could transition between these allowed energy levels by either absorbing or emitting a photon, a little packet of light energy.
So like a tiny burst of light.
Exactly. And the energy of this photon is precisely equal to the energy difference between the atom's initial and final energy levels. If an atom absorbs a photon with just the right energy, it jumps up to a higher energy level, an excited state.
And when it drops back down to a lower energy level?
It emits a photon with that exact energy difference corresponding to a specific wavelength of light.
So that's why atoms only emit and absorb light at specific wavelengths, because of these energy jumps.
Exactly. And Bohr focused his model on the hydrogen atom, the simplest one with just one proton and one electron. What were his key assumptions for this model?
Well, for the hydrogen atom, Bohr said that the electron orbits the nucleus in specific circular paths. And crucially, the angular momentum of the electron in these orbits is also quantized.
Quantized, meaning what?
It can only take on specific values, not any arbitrary value. He said it has to be an integer multiple of h bar. So it's like the electron can only occupy certain allowed orbits, not just any old path.
And this idea of quantized orbits, what did it lead to?
Well, using that and classical laws with some tweaks, Bohr figured out equations for the radii of the allowed orbits, the speed of the electron in each orbit, and most importantly, the energy levels of the hydrogen atom.
Wow, so he could actually calculate these things.
He could. And his calculations lined up amazingly well with the observed spectral lines of hydrogen. When an electron transitions between energy levels, the energy of the emitted or absorbed photon matches perfectly with the energy difference Bohr predicted.
So his model actually explained the real-world observations.
It did, and it did it for different series of spectral lines too. Transitions to the ground state, which produce ultraviolet light, transitions to the second energy level, producing visible light, and so on.
What a triumph.
It was. And you mentioned fluorescence earlier. How does this model explain that? When something absorbs light at one wavelength and then emits light at a longer wavelength.
Fluorescence is all about those energy level transitions. Let's say a material absorbs a photon with a lot of energy, causing an electron to jump way up to a high excited state. But instead of falling directly back down to its original level, the electron might cascade down through a series of smaller energy transitions. It might lose some energy as heat and then drop to lower levels in stages, emitting photons with lower energies at each step.
So lower energy means?
Longer wavelength. That's why the emitted light in fluorescence has a longer wavelength than the light it absorbed.
It's like absorbing a big energy jump and then coming down in smaller steps.
A great way to put it. But you did hint that while Bohr's model was a huge step forward, it wasn't perfect. What were its limitations?
Well, as good as it was for hydrogen, it struggled with more complex atoms, ones with multiple electrons interacting. It also couldn't perfectly explain things like the relative intensities of the different spectral lines or the fine structure, those tiny splittings in the lines when you look closely.
Right, so it was a stepping stone, a crucial one, but ultimately it paved the way for the more complete theory of quantum mechanics.
Okay, now let's move on to something that always seems a little bit sci-fi. Lasers.
Definitely rooted in science, though.
Absolutely. Based on these quantum principles we've been discussing. So what is a laser and what makes it special?
A laser stands for light amplification by stimulated emission of radiation. It's a device that produces a beam of light that's unlike any other. It's coherent, meaning the waves are all in sync with each other.
Okay.
It's almost completely monochromatic, just a very narrow range of wavelengths, and it can be super intense, focused into a tight beam. It does all this by using the cooperative emission of photons from a whole bunch of atoms.
And you said stimulated emission is key to how it works. How's that different from the usual way atoms emit light?
The usual way is called spontaneous emission. That's when an atom in an excited state randomly drops back to a lower energy level, emitting a photon with random direction and phase.
It just happens spontaneously.
Yeah. But stimulated emission is different. It happens when an incoming photon, with energy matching the energy difference between two levels in an atom, interacts with an atom that's already in the excited state. This incoming photon basically triggers the excited atom to drop down and emit another photon that's an exact copy of the incoming one. Same energy, same phase, same direction.
It's like a chain reaction of light.
Exactly. Think of it like a room full of people humming quietly. If someone starts singing a note, it can trigger others to start singing that same note in the same rhythm and volume.
So one photon in, two identical photons out. That's the amplification part.
You got it.
But how do you get all those atoms into the excited state in the first place?
That's where population inversion comes in. Usually, most atoms are in lower energy states. But to get a laser, you need more atoms in a higher energy state than a lower one. This isn't the usual state of things. It's achieved by pumping energy into the laser's material to excite those atoms.
Like giving them a boost.
Exactly. And you mentioned a 4-level laser being more efficient. What's the advantage of that?
Well, with just 2 energy levels, it's hard to maintain that population inversion for long. A 4-level system is more efficient, atoms are pumped to a high level, and then they quickly drop to a slightly lower, more stable level.
A metastable state.
Right. Because it's more stable, a bunch of atoms can hang out there, creating that population inversion we need. When a photon with the right energy comes along, it triggers those excited atoms to emit identical photons.
And those emitted photons trigger even more, causing a cascade of photons all identical.
So what's the purpose of the mirrors at the ends of a laser? That resonant cavity.
That cavity is formed by 2 really reflective mirrors, one of which lets some light through, Photons traveling along the cavity bounce back and forth between these mirrors, and each time a photon passes through the material, it triggers more stimulated emission.
Amplifying the light.
Exactly, making the beam more and more intense. The partially transparent mirror lets a portion of that amplified light escape as the laser beam we see.
And there are different types of lasers, right? Depending on what material they use.
Yes, we have gas lasers, solid-state lasers, and semiconductor lasers, each with its own characteristics. They can emit light continuously or, in short, powerful pulses.
And all from the idea of quantized energy levels.
It's remarkable.
Now, let's switch gears again and talk about the light emitted by hot solids and liquids. You said they produce continuous spectra. Unlike those distinct line spectra from gases, why is that?
Well, in gases, the atoms are far apart. They don't interact much, so they have those well-defined energy levels like Bohr described.
Okay.
But in solids and liquids, the atoms are jammed together, they interact strongly, and that makes their individual energy levels blur together into continuous bands of energy.
So instead of discrete steps, it's more like a ramp.
A good way to visualize it. Because the electrons in these materials have a whole range of energies available, they emit photons with a continuous range of energies. That's what makes a continuous spectrum.
Makes sense. You mentioned the concept of a black body. What's that exactly, and why is it useful for understanding these continuous spectra?
A black body is an ideal object that absorbs all radiation that hits it. No reflection, no transmission, just pure absorption. And because it's a perfect absorber, it's also a perfect emitter of radiation when it's heated. The spectrum of light it emits, called blackbody radiation, depends only on its temperature, not what it's made of.
So it's a theoretical model?
Yeah, a useful one for understanding thermal radiation in general.
And there were some laws describing this blackbody radiation even before quantum mechanics, right? Like the Stefan-Boltzmann law and Wien's displacement law.
Right. The Stefan-Boltzmann law says the total intensity of radiation from a black body is proportional to the fourth power of its temperature.
Meaning?
If you double the temperature, it emits 16 times more energy.
Wow.
And Wien's displacement law tells us about the wavelength where the radiation is most intense. This peak wavelength is inversely proportional to the temperature.
So as an object heats up, the peak of its emission shifts towards shorter wavelengths. That's why things glow red, then orange, then yellow, and eventually white as they get hotter.
Exactly.
But classical physics had trouble explaining the entire shape of that blackbody spectrum, right? Especially at the shorter wavelengths.
It did. They tried to derive a formula to predict how much energy is radiated at each wavelength, but it predicted the intensity should become infinite as the wavelength gets shorter, especially in the ultraviolet. They called this the ultraviolet catastrophe.
Catastrophe because it didn't match reality.
Yeah, the experiments showed that the intensity actually goes to zero at very short wavelengths. Classical physics just couldn't explain it.
So, enter Max Planck and quantum mechanics.
Precisely. Planck made this radical proposal that energy at the atomic level isn't continuous. Instead, it's bundled into these discrete packets called quanta. We now call them photons.
Photons, packets of energy.
Yes. And he said the energy of each photon is proportional to its frequency or inversely proportional to its wavelength. This revolutionary idea led him to a new formula for the blackbody spectrum.
And it worked.
It worked beautifully. It perfectly matched the experimental data, and it resolved that ultraviolet catastrophe. And even the Stefan-Boltzmann and Wien's laws could be derived from Planck's law.
So, a big win for the idea that energy is quantized. Okay, one last thing we need to cover. The Heisenberg uncertainty principle. This is where things get really strange.
It's one of the most profound consequences of wave-particle duality.
Right. Particles act like waves. And that seems to put a limit on how precisely we can know certain things about them. Tell me about it.
The uncertainty principle, formulated by Werner Heisenberg, says there's a fundamental limit to how precisely we can know certain pairs of properties for a particle at the same time, like its position and momentum.
So the more we know about one, the less we can know about the other.
Exactly. If you try to pin down a particle's position super accurately, you disturb its momentum in a way you can't predict. And the more you try to know about its momentum, the less you know about its position.
It's like nature's keeping some secrets.
In a way, yes. And it's not just position and momentum that are linked like this. There's also a relationship between energy and time.
Okay, tell me about that one.
The energy-time uncertainty principle says there's a limit to how precisely we can know a system's energy and the time interval over which we measure it. This means, for example, that atomic energy levels, even those seemingly sharp ones, actually have a tiny bit of inherent uncertainty.
So even in the quantum world, there's a bit of fuzziness.
There is. And the uncertainty principle shows us the limits of Bohr's model. It imagined electrons orbiting with specific positions and speeds at any moment. But the uncertainty principle says we can't know both those things perfectly at the same time.
So Bohr's model was a bit too neat and tidy.
It was. It's why quantum mechanics had to come along. It treats electrons not as particles with definite paths, but as waves described by probability distributions.
It's almost like the universe doesn't want us to know everything for certain at those tiny scales.
It's a truly mind-bending concept, but it's been incredibly successful in explaining so much about the universe.
It really is amazing how it all ties together. From the wave-like behavior of electrons to those beautiful atomic spectra, lasers, the light from hot objects, and the limits of what we can know, it's all connected through this idea of wave-particle duality.
It makes you wonder how this inherent uncertainty at the quantum level shapes the world we see at larger scales. What does it mean for what we can ultimately know about the universe?
A question for another deep dive, perhaps. But for now, thanks for joining us on this journey. We covered a lot of ground. And until next time, keep exploring the fascinating world of science.